So what I'm going to talk about today is how snow lines, so these are the regions where chemical condensation changes, so water freezes out from vapor to solid, or CO freezes out from vapor to solid, are not actually passive fixed position lines that occur in protoplanetary disks, but they can actually be incredibly dynamic and perhaps even drive some of the dynamics of protoplanetary disks. So the motivation for this talk, or one of the motivations for this talk, is recent ALMA observations in the continuum, which I'm showing here on the right from this wonderful gallery from the D-SHARP survey, show beautiful ringed structures in many protoplanetary disks. Now, one of the major origins of this is perhaps a planetary origin, but in this talk we're going to consider alternative origins and perhaps explore a more mundane but equally interesting chemical origin. And not only have we been able to image protoplanetary disks in the continuum and look where the dust components are, but we've also been able to image gas tracers in protoplanetary disks. So I'm showing here on the left an ALMA image of N2H+, which is believed to trace the position of the CO snow line. So outside the CO snow line we see lots of N2H+, and inside the CO snow line we see no N2H+. So we're actually able to learn about the chemical composition and chemical evolution of these disks from ALMA observations. Now, while the planetary hypothesis to these rings is very alluring, one of the original ideas was actually perhaps that snow lines where solids condense into the vapor phase, or vice versa, cause sort of changes in the abundance of solids as a function of distance. And one of the perhaps hints of this was that if you compare the surface density profile of HL Tau, shown here in black, against the position of various snow lines, then the positions of features in the HL Tau famous ringed image appear to align with perhaps where these snow lines may lie. And on the right here I'm showing the dust to gas ratio as a function of position at the CO, CO2 and water snow line, and this is simulations from Richard Booth showing that these snow lines indeed do cause large changes in the surface density of solids around their position. So perhaps there's something to this idea. But in all previous work, snow lines have been treated rather passively. The temperature profile of the disk has been fixed, and then wherever that temperature profile crosses the phase change curve for these snow lines, the snow line occurs. But the important thing to remember about protoplanetary disks is that the disk temperature depends on the distribution of solids, but also the distribution of solids via these snow lines depends on the disk temperature. So this process is intimately coupled, and it's not clear, in fact I will show, that it's not actually stable. So as a bit of revision, we're going to go back and remind ourselves what sets the temperature of the disk. So we have our star, which heats the surface layers of the disk, and this reprocessed stellar radiation then heats the midplane of their disk. So if we zoom in a little bit and consider what's going on in more detail, we have our stellar photons coming in, and it's being absorbed by small dust particles in the surface layers of these disks. Because these dust particles are small, smaller than the wavelength of the light they're emitting at their temperatures, they're very inefficient emitters, and they're very inefficient coolers. So they cool via longer wavelength radiation, and because it's very inefficient, this results in a superheated dust layer. But this escaping radiation from the surface layer doesn't just leave the surface of the disk, it also goes down and heats the midplane, where there are plenty of solid particles, large solid particles, that are actually much more efficient coolers than emitters. So we actually end up with a cool midplane that cools via even longer wavelength of radiation. So the important concept is the radiation that heats the midplane is hotter than the radiation which cools the midplane. So it's not a gray system. We need to include non-gray radiative transfer. So if you look at how the opacity changes as a function of the temperature of the radiation, as the temperature of the radiation increases, so does the opacity. So this means the optical depth to the incoming radiation is much higher than the optical depth to the cooling radiation. So why is this important, and how does this affect the snowline? Well, let's consider a few scenarios of the snowline. Imagine we're at the snowline and we have our volatile in the solid phase. If we're optically thick, then the heating rate is independent of density. Basically, all the incoming stellar radiation from the surface layers I absorb, and the cooling rate is also independent of density. Because I'm optically thick, I just cool as a black body. So if I change my density, I absorb all the heat radiation from the surface, and my cooling rate doesn't change. So my heating rate and my cooling rate doesn't change. My temperature is unchanged. Now if I go to the completely other limit, the very optically thin limit, then the heating rate depends linearly on density. If I double the amount of material in my midplane, then I double the amount of the radiation I intercept, and the same for the cooling rate. If I double the amount of material, then I just double my cooling rate. So in the optically thin limit, again, the temperature is unchanged as I change my density. But if I go to a marginally optically thick limit, where I'm optically thick to the incoming radiation, but still optically thin to the cooling radiation, then in that case the heating rate is independent of density. I change my density, I still absorb all the incoming radiation, but the cooling rate depends linearly on density. So this means if I reduce my solids, then my heating rate stays the same, but my cooling rate goes down. So my temperature heats up, and I melt more solids, which reduces my surface density abundance again, and I heat up further, so I run away. If I do the opposite, if I increase the number of my volatile species in the solid phase, my cooling rate increases. Remember, my heating rate is still fixed, so the temperature goes down and I condense more solids. So this means that snow lines are thermally unstable at intermediate optical depths. And we can look at that more precisely if we plot the heating and cooling rates as a function of temperature at various optical depths. So at low optical depths, there's only one solution of the snow line, where heating balances cooling. Same at very high optical depths, there's only one point where heating balances cooling. But at intermediate optical depths, there are 3 points where heating balances cooling. And the solution at the snow line, this open circle here, is thermally unstable because the rate of change of the heating rate, the solid line, with temperature is much higher than the rate of change of cooling rate. So if I were to perturb my temperature, I just run away to this point or this point. So how does this manifest itself in a real disk? Well, at real snow lines, depending on whether I'm in the solid phase or the vapor phase, the flux of these volatiles is going to be very different. If the volatiles are in the solid phase, in ices, in solid particles, they're going to drift with respect to the gas due to radial drift very rapidly, and they're going to drift inwards. Whereas if they're in the vapor phase, then they're just going to flow in slowly with the gas. So not only do I have multiple solutions, but at those multiple solutions, then I move at different rates. So how does this manifest itself in a real disk? Well, to do this, we're going to run some numerical simulations. So what we're going to do is we're going to take a radiative transfer model that calculates how the temperature of the disk evolves as I change the surface density of the solids, and I'm going to couple this to a model that accounts for radial drift, grain growth, but also importantly for what happens at these snow lines, how I transition from the vapor phase to the solid phase and vice versa. So I'm about to show the results from this simulation. So this is a video here showing the surface density on the left as a function of distance in the right. And we're going to look at just the CO snow line here. So the various lines, the blue dashed line shows the CO vapor, the orange line shows the total abundance of solids, and the green dotted line just shows the abundance of solids that don't include CO ice. So at the CO snow line here, we have a very rapid change in the total solid abundance. So if I let this system evolve, so in the standard picture where the temperature is fixed, then this snow line just remains at this same location forever. But if I let it evolve, I see that the snow line actually moves inwards and outwards as the disk goes through these thermally unstable phases. And if you're interested, you can actually describe this thermal instability in terms of the standard S-curves that you did for other types of accretion disk thermal instability. So what we can see is the snowline moves over several tens of AU, increasing the surface density by a couple of orders of magnitude, and also, interestingly, introducing these kinks in the surface density inward of the snowline that propagate inwards. Now, these moving snowlines also cause shadowing, repeated shadowing of the disk. So this is a plot of the photosphere height as a function of position. So any point where the photosphere goes down as you go out is going to be shadowed. So this can introduce extra temperature structures from this shadowing in the disk, and perhaps multiple rings. So in summary, snowlines are subject to a thermal instability at moderate optical depth. So most of these snowlines we'll be observing with ALMA should be subject to this, like the CO, CO2, and ammonia snowlines. Snowlines evolve through a limit cycle in the outer regions of protoplanetary disks, where the snowline moves in and then out. And for the CO snowline, it can move tens of AU in 1,000 to 10,000 years with dramatic changes in the solid surface density. And in future work, we're going to extend this to multiple snowlines in an evolving disk and see how a disk actually chemically evolves as an